the whole purpose of quaternions is to be able to do with vectors what we can do in the complex plane with complex numbers. And one of the most important things then is to be able to do rotations. And the ability of quaternions to represent attitude hinges on the possibility of expressing the rotation of a vector by means of the quaternion product. So we have a rotation formula that I'm going to spell out. So let's say that this is a quaternion. And now I'm going to assume that this quaternion can be linked to some numbers, a number alpha and a vector n, according to this. So I assume that this has to be a unit quaternion with one unity, and then that there is some number alpha and a vector n, so that this holds. Of course, this quaternion has a scalar part and a vector part. I'm going to use that notation too, so keep that in mind. And then I claim that it's possible to write the following. So what you have here is vector v, and you have another vector v marked. And then I've inserted those in the vector slots in a quaternion, and then I've done first I pre-multiply with the quaternion, given by this, and then I post-multiply by the conjugate quaternion. And then my claim is that this is the same as stating that v marked is the rotation of vector v around the vector n alpha radians. So this is my nice quaternion rotation formula that enables me to use quaternions as an attitude representation. So then I would like to prove that this holds. So we're going to have a strategy consisting of three phases. So the first phase is that I'm going to do the quaternion product, spell it out. What is this in terms of vector and epsilon, the vector and scalar parts, and this vector v that I'm trying to express first. Then I'm going to look at these expressions, and I'm going to recognize trigonometric expression in the angle alpha. Once I've done that, I then hope to be able to relate this to the angle axis representation, which is the most fundamental attitude representation that I'm working with. So those are the three steps I'm going to go through. So I'm going to start now. I'm with spelling out the details of the quaternion product. So let me first take this part. So the V times the conjugate quaternion. So in the conjugate quaternion, I have the same scalar part, but I subtract the vector part, same as I would do for a conjugate complex number. And then this is what I get from the standard quaternion multiplication formula. No contribution from combining the scalar parts, but this vector part together with the V will enter it. And then I have this vector part times the scalar part, and then I have the cross product of the vector parts. So then I do the full product, also including the Q over here. And things get a bit more complicated. So I'm going to take the original quaternion times this whole thing. First I have this scalar part times this scalar part, then I need to do the scalar vector cross terms. This one times this. Then I'm going with the new scalar part, so look at the new vector part. So I have this one times this one. Then I need to see what I get from combining this one with this one. And finally, there is the cross product between the two vector parts. So, somewhat nasty expression I have here. So this I would like to simplify, and this can be somewhat simplified. Now the scalar part is what I can simplify most. Now if I look at what I have here, I have this epsilon times two different factors, or two different terms in the second factor. So now I look at the second term here. This is a cross product between V and epsilon, so I know it's perpendicular to both of those two, meaning it's perpendicular to epsilon, and a scalar or inner product of perpendicular entities is 0. So then I'm left with epsilon times eta v. To see that this becomes exactly the same here, because both are scalars, order doesn't matter, it's commutative for inner product. So they're going to cancel, and I'm left with 0 dette her. So for the vector part, the first term we can't do very much with. Then I have some eta times eta, okay? I can write that as eta squared. And then I have an eta times v cos epsilon. Do I have that anywhere else? Yeah. Here I also have a cross product between epsilon and v. If I flip the order of epsilon v, it's going to be minus, so it means they're going to have the same sign. So I can write this as 2 epsilon, so 2 eta epsilon cross v. So what am I left with then? So I have this times this. Yeah, I'm left with this cross product, which I would like to write as something else than a cross product. I would like to reduce this also to inner product. This can actually be achieved if I change this plus to a minus. And use this trick. So what you see here inside this big parenthesis is simply the same as this double cross product. This is one of those identities that you probably can find in Rotman or Wikipedia, wherever you search for it. So then I got rid of the double cross product. I have a single cross product here. And I have some nicer terms here. So let me now just reorganize this a little bit. Keep the 0 up here in the scalar part. And now I have this term. I also have a very similar term over here, so I can combine those. Then I have this term. I'm not going to do anything more with that one. Epsilon cross v. And then I have all the things that I'm multiplying with the v vector. So that's an eta squared. And then I have this thing, which is the same as the norm of epsilon squared. Now it's time for me to think a bit about going into the second phase. I have gotten as far as I could get in the first phase of the proof. now it's time to think about what eta and epsilon are in terms of alpha and n. So, if I have now this scalar here, what does this become? Eta squared minus norm squared of epsilon. And that is cosine alpha half squared minus sine squared alpha half. So what is this? Well, we can check what one, page 87 should be, or Wikipedia or whatever. Whenever you see something like that, you check one of those standard references to see if there's anything you can do with it. Indeed there is. This is just cosine to alpha. So do we have any other nasty expressions we would like to do something with? We have this one. V transpose epsilon times epsilon. Yeah, I need to get rid of those epsilons. So, in the epsilon, I have sine alpha, so again, I'm going to get the sine squared. Then I have my V and N. This is supposed to be a vector proportional to N. Again, it's here I have these half angle formulas I find in Rotman. I don't want to have half an angle, I want to have the same as here. I got rid of the half an angle, I got just cosine of alpha. So I can do the same here. That also worked out. Then I'm left with the cost product. I must be able to do something similar with the cost product too. This is the cost product that we need to do something with. Now I have both a cosine and a sine half angle. And then I'm left with my n cos v. So again, Wikipedia, Rotman, then it becomes sine. So then I have finished phase 2 of the proof. I have gotten rid of all my epsilons and etas and gotten everything expressed in terms of alpha and n, and also I have gotten rid of the half angles. Now it's just sine angle, cosine of alpha. Then I look at my axis angle formula. So if I have formula again, you have the rotate vector V mar. Then is my 1 minus cosine alpha. Inner product NV times 10 plus cosine alpha times V sine alpha and cos C. Okay, this one goes there, this one goes there, this one is the same as this one, which of course is to be multiplied by the V. So what you see now is that the vector part now of this double quaternion product in V is exactly the same as I will have from using the axis angle formula with alpha and n as my angle and axis in the amplitude representation. So in other words, they are equivalent, and I've shown that this quaternion product indeed rotates vectors the way it was supposed to do.